Welcome to Analysis 1A lecture. I don't even know. Is this 9 or 10?
9.
You think it's 9?
9.
I'm pretty sure it's 9. We have only a 45-minute class today. Thank you, because of some school functions. So let's do it. I would like to do 3 things today. One, I'd like to go over homework. The homework was a lot, and it was difficult and interesting. And so I'd like to go over, in theory, tons of the problems, but in actuality, just a couple of them. Which ones did you find difficult? Let's see if that matches up with the ones I think you were going to find difficult.
I have 76, maybe.
76, yeah. What else? 63 and 65. I'd like to go over 65. I thought 103 from the previous section was difficult. This was the problem I think I warned you about in advance, right? And maybe also we do 113, and maybe that's as far as we get. I'd like to go over 77 also. I don't know. Let's see. I'll go fast. Hey, Kumar. Thank you. Yes, very much so. Okay, so 103, very exciting and technical problems from the previous section. This is when we were still talking about the definition of the derivative, and what it did was to introduce you to 2 functions. One of these functions is x sine 1 over x, when x is not 0, but plug the hole with a 0 when x is 0. So piecewise function. And a second kind of related piecewise function is the one which is x squared sine 1 over x, when x is not 0, but 0 when x is 0. Okay, and now you're being told to do a bunch of things with these functions. In particular, show that f is continuous but not differentiable at 0, and show that g is differentiable and find the derivative. Okay, so technical problem. This is testing your ability to to know the exact technical definition of continuity. So first, let's show that f is continuous at x equals 0. What does it mean to be continuous at a point? Laura?
The limit is to that point is equal to the value of that point, and that it exists.
Yeah. We have to show that the limit as x approaches 0 of f is equal to f of 0. Well, okay, what is the limit as x approaches 0 of this f of x function? Yeah, it is 0, right? Because I can just say that this is the same thing as the limit as x approaches 0 of x sine 1 over x, because that's the rule that we're following everywhere except 0, and 0 is irrelevant. And what is this limit? Everybody? 0 by the squeeze theorem. Okay, yeah, so we're just like experts now, right? Without even writing out all the details, I can squeeze x sine 1 over x between x and negative x, and so this limit is 0. So that's check. The limit does exist at 0. And then also just like, what is f of 0? It's 0. Yeah, and we know something about this function f because we've done this a million times. We know that this function is going to look, this is what I now call the mustache function, which has a limit of 1 and is even and kind of does this, right? Goes crazy near 0, but is squeezed to 0. Okay, so indeed, this function has a limit at 0 at 0, and it has a value at 0 at 0. Those are equal, so this function is continuous. Check, do you agree? All right, now we must show that f is not differentiable at 0. So what is f prime of 0? Well, I certainly don't have a rule for such a crazy monster at this point, so I have to do it using the definition of the derivative, which is all you knew at this point in the section of the textbook anyway. All right. So f prime of 0, I guess the simplest thing to do is to say, well, it's the limit as x goes to 0 of f of x minus f of 0 over x minus 0. And, right, is this what you guys did? Basically, you either did it this way or you did it the other way, but it works out to be the same thing because this is the limit as x goes 0 of, well, f of x is basically x sine 1 over x everywhere except 0, which is irrelevant. And then f of 0 is just 0, and this is just this. So it turns out that f prime of 0 is the limit as x goes to 0 of just sine 1 over x. And what do we have to say about that limit? Correct. This limit does not exist. And since this limit does not exist, my conclusion is that f prime of 0 does not exist. Again, we talked this all out informally. Now here's the formal proof that since a derivative is defined to be a limit, if that limit does not exist, and we've talked previously about why this limit doesn't exist, so I'm not going to get into that all over again. And so, does anyone want to talk about kind of what that sort of means in light of the graph that we have here? Why does this derivative not exist? Or just this is like now you know there's no, we've done the technical proofs. Now you just discuss your like thoughts, feelings. Poetry would be appropriate in this juncture.
Perhaps it has an undefined slope of 0.
It has an undefined slope at 0. Okay, that's a start. Yeah. Yo.
I think, yeah, because it's an even function, it's doing like its slope is like doing one thing on one side of 0 and like 0 plus, and then on the other side, on 0 minus, it's like going like a completely different direction.
Is that a thing?
Sounds like it makes
I
some
don't feel like that's a
sort of
problem
sense.
because like y equals x squared is also even, and it's also its derivative is odd. So I don't think that's not a problem. I don't think even an oddness is an issue. What's going on? Just talk to me. Just share your thoughts, words. Yeah, Emma.
It's going like, we don't even know what it's doing.
Like, what is the line doing? Like, it just like.
Yeah, so we can just kind of follow along the path with our pencil or whatever. It's kind of just like the derivative is like the slope, right? What's it sort of doing at 0? What's it doing?
Insane stuff.
Yeah, kind of just like, right? This function, the sine 1 over x function, is the one that goes up and down like crazy, right? This one's trying to go up and down like crazy, but it's being squeezed. It's being squeezed in, so it's still going up and down like crazy, but it's just not getting very far. I feel like we've talked about this function like 5 times, right? This is like the man, this is like the crazy man in a straitjacket. Have I made this analogy before? Yeah.
I think so.
I think so. Or maybe Tees were wearing it from 2 years ago. Yeah, so anyway, to me it seems like the guy is moving in different directions at an extremely rapid rate. He's not getting anywhere. What else? Let's move on. What's the other thing we're supposed to do? We're supposed to show that G is differentiable. Okay, well what is G prime of 0 by definition? Well, G prime of 0 is by definition the limit as x goes to 0 of g of x minus g of 0 over x minus 0. So that's the limit as x goes to 0. Well, what is g of x? It's x squared sine 1 over x minus g of 0, which is 0, over x. Well, this is the limit as x goes to 0 of x sine 1 over x. And what is this limit? 0. And in addition, so this function does have a derivative. And we can make a graph of what this function looks like. This function is now contained within a parabolic envelope. And we've also seen that it kind of goes off. It's odd, it kind of does like something like that. So do you guys sort of like feel this? Talk to me now. Why? Then now this guy is 0 there. What's going on? Okay, here's him again.
Okay, so on the top one, the sort of like sine oscillations are getting steeper and steeper and steeper until like sort of like infinitely steep in the middle. Whereas on the other one, it's kind of getting infinitely less steep and less steep and less steep until it gets like flat, sort of at 0.
Yeah, the frequency of the oscillations is every bit as crazy as it was before. But now it's like we dropped a big fat like parabola mattress on it or whatever and just kind of like made it like really flat. Arun, you have something to say? Student name, contribution. Yeah.
Can derivatives be squeezed in a similar way? Like here,
yeah, I guess,
both the
right?
top and the bottom have a slope of 0 for the parabola, but at the top they have 2 different slopes. So when you squeeze the middle function's derivative with the upper and lower derivatives, then at the bottom you get 0, but at the top it's undefined.
Yeah, that sounds like that could be a theorem or something. There's probably not going to discuss that right now, but yeah, right? I mean, whatever the derivative of it is, it has to be somewhere between the derivatives of the 2 parabolas. Yeah, I agree. Okay, cool. That was like, should have taken us 1 minute and took us 8 minutes. Good job, me. Let's do more problems. 65. Now we actually know some derivative rules, so that's really good because it means that we can do things kind of fast. And did you guys get my note on headline where I said, hey, by the way, this works not only for polynomials, it works for any kind of power to be proven later. We're going to do it that way just because that's how the book does it. So here was this problem, somewhat high-level, multi-step thinking problem. A function was given to you, a function with a unknown sort of parameter k, and then you're also given this line, y equals -3/4 x plus 3. I love these kinds of problems, and so does the book, because they really test your understanding. What are we supposed to do? Find k such that the line is tangent to the graph of the function. Okay, let's make a picture. That is like the step one of what you do in calculus, always, always, always. Make a picture. So let's do that. This is like algebra 1. This line has just a 3 and slope -3/4, so like down 3 over 4. So I'm feeling really confident about my line drawing skills. There it is. Now I have to draw the function f of x equals k over x. Okay, well let's just suppose k is something pretty like 2 or something like that, right? Then it's going to be like a jump and a jump. In fact, I say k must be positive because in order for, when k is positive, it lives in quadrants 1 and 3, and it just has to because like look at my picture, right? With me? Okay, so now I'm going to draw some kind of something like that. How's that go? Is that pretty much what k over x looks like? Yeah, thank you. There's some point at which this line is tangent to this curve, and I don't know. Let's talk about all the things I don't know. What's one thing I don't know?
Don't know that point.
I don't know that point. What's another thing I don't know?
The slope.
The slope. What's another thing I don't know? Someone said it.
K.
K. I don't know K, okay? So I don't know what K is, and I also don't know what that point is, and I also don't know what, no, I guess I do know the slope of the line, right? The slope of the line is -3/4. In fact, I'll even just mention that. Okay, so somehow using logic and things and derivatives are probably relevant. We need to figure out what this point is, we need to figure out what K is. That's the problem, right? Okay, good, what do we do?
Set stuff equal to each other.
Set stuff equal to, yeah, first maybe, abuses.
Derivative of f of x, like for any x.
Oh, let's just take the derivative of this function. That seems like a good idea. Watch how easy this is. F of x equals k over x. First we do this step in which we rewrite the function in what I call a derivative-friendly form. So a derivative-friendly form would be to express this as kx to the -1. And though I have not proven it yet, the power rule which we derived last class also works for negative exponents. Just trust me for the moment. Okay, so if we differentiate this, then using the power rule, I just get k times negative x to the -2. Yeah? Then I take my derivative and I rewrite it in a algebra-friendly form, which to me means getting rid of negative exponents. So that's the form that I'm pretty happy. Okay, great. What does that get me? Uses again.
Well, you know that that has to be the
Let's-
slope because that's the derivative of your point, and the slope, the tangent line to that point. Is
Yeah, okay, but let's just be a little careful. I'm sure you get it, but you're not saying exactly because the derivative is a number. This is the derivative function. So it doesn't make any sense to say that the slope of this line is this, because this isn't even a number, this is a function. So what do you really mean? Calvin?
That at any point on that, that's what the slope would look like. And
At any
that
point on this curve, that's what the slope is. Yeah, I agree.
But at that exact point, the slope is -3/4.
At that point, yeah. If only we had like some name for that point, then we could actually have whole
Yeah.
sentences. Like it would be like if you just had a bunch of children, you just called them like kid every time. Like that's not really good, right? Then no one knows who's being spoken to. Some people do that. They call their dog just like dog. That's usually like means something. Yeah.
The point where f of x equal and the line intersect.
Tangent.
Well, no, when they have like the
Wait,
same.
what?
The happy
but-
point.
I thought I was making like a joke, but you guys don't seem to be following on. Can we just like call this a name? Just give it a name. Pick a letter.
Hey.
Hey, okay, thanks. Yeah, that's all. That's all I was looking for was just to take the initiative to temporarily give a name to a thing that you do not know. That's all I'm asking you to do. So if we call this A, then what's the y coordinate of that point?
K over A?
K over A, because of course that point must be on the curve. Everybody with me?
Yes.
All right, now that I've called this point A, now I can tell you what the slope of this line is. What is the slope of this line? Now, Bucis Calvin. It is -3/4, I agree, but also
It's k over a.
negative k over a squared, right? Because the slope of this line has to be whatever, if this line is indeed tangent to this curve at this point, then the slope of this line, while it is negative 3/4, must also be the f prime of a, which we know to be, by our calculations, negative k over a squared. Maybe this problem's not that hard. Did you guys find this hard? I don't know. No? Yes?
Yeah.
Why is this negative k over a squared? Because this derivative function is a function which will tell me for any given point what the slope of the tangent line to the curve is.
Oh.
That's what the derivative means. So now that I've temporarily named this point a, then if I just plug a into the derivative function, it outputs the derivative, right?
Why is the arrow pointing at the line and not the curve?
Why is my arrow pointing at the line? Because the slope of this line is negative k over a squared. We define the slope of a curve to be the slope of the tangent line to the curve. Right, so it's the same thing. Okay, so what this yields is at least one equation. The equation that the slope is negative 3/4 and is also negative k over a squared. Is this what you guys did basically? I think it's probably almost is exactly if you solved it. Okay, what else? There's one more key fact which is like necessary. Just slightly subtle, yeah, random.
The point tangency is also an intersection, so you can set the y values equal to.
Yeah, it's also true that it being a tangent line means that both the line and the curve go through this point. So whereas because the first person who spoke said it's k over a, it's also true that that point must be a comma, well it must be negative 3/4 a plus 3. Are you with me? Because I have to get the same thing. So I have that the y, essentially I'm setting up two equations. One that says that the slope of the line has to be equal to the derivative at the point, and also that the y-coordinate of the point on the function has to equal the y-coordinate of the point on the line. So we get negative 3/4 a plus 3. I should have asked before we started this problem. Right now, if you got this, you figured out the whole problem by yourself. Okay, so this is like half, no, it's more than half, 2/3 of the class. Mateo, you got this now?
Yeah.
Yeah, and now I just have to solve this system of equations. I don't know, should we do that or just like move on?
Yeah.
Maybe I'll just go really fast.
Yeah.
So what do I do? Like solve for k or something? So
No,
Or
no,
negative k
just,
over a.
Just do k over a. Just multiply by negative
Yeah.
a. So
really? Oh yes.
Yeah.
Ooh, getting smart suggestions from the audience. Yeah. So from the first equation, it's true that k over a is 3/4 a, and from the second equation, it's true that k over a is negative 3/4 a plus 3. Ooh, this person knows algebra. And so those two things have to be equal to each other. So I get 3/4 a equals negative 3/4 a plus 3. Hit that with a 4. And stuff happens. Do we get 2? Is that what you got? No one's saying anything. I mean, yes? Yes, good. If a is 2, then suddenly everything becomes clear. What must, or does everything become clear?
Yeah.
If a is 2, then what's k?
3.
It just must be 3, right?
Yeah.
Because, yup, then k must be 3. Bam, done. Okay, I'm feeling okay about that. All right, let's do like 2 more problems. Let's do 76 and 113. When do we have, what's the 45-minute mark of this class? Like, it would be like 12,
minus 45.
12:25. Oh, we're good. So we got plenty of time.
Says we have.
76. Let's do that. It's another multi-step kind of problem. Raise your hand if you got 76. I guess you don't know. I thought that was maybe not quite so hard. 76 presents you with a function f of x equals x to the 5th plus 3x cubed plus 5x. And then tauntingly says to you, show that this function does not have a tangent line with a slope of 3. Okay, well, I don't know, what should we do? Yeah, Laura.
The derivative.
Just take the derivative. Yeah, okay, let's just do that. I don't know why yet, but it does seem like a good idea. So I take the derivative, I know how to do that. Bam, so fast. Okay, Laura, keep going.
And now you just know that it can't because it's plus 5, right? And those are both even powered, so the derivative always has to be greater than or equal to 5, and so 3 is kind of not an option.
Yeah. Okay, I'll take it. Right? Yeah, that's pretty much it. The slope of the if the slope of the tangent line to the curve is somewhere 3, then the slope of the tangent line to the curve then the derivative would have to be 3 somewhere. But if we take the derivative and set it equal to 3, we see that this equation just has no solutions. because this is always positive, that's 5. So in fact, she said something even deeper. She said that the slope of this, the derivative of this function is always greater than or equal to 5, right? Yeah. So actually, that says something kind of deep about this function. Do I want to try to graph it? No, I don't feel like it. But this function's always pretty steep. And also, someone wants to say something else deep about this function. If the derivative is always greater than 5, I won't make any subsequent comments or anything, but if you would like to just tell me something about that function, then therefore. Okay, not the same 3 people. Okay, yeah, you talk today. What's up?
It approaches infinity as x approaches infinity and negative infinity as x approaches negative infinity.
That's true, but I kind of knew that about polynomials anyway. But specifically that the derivative is positive. That if the derivative is always positive, if you don't know the answer to this, it's fine. I haven't taught this to you, but it's semi-common sense. If the derivative is always positive, and in fact is greater than 5 Mateo.
Is it always increasing? Is that right?
Yeah, it must always be getting bigger, right? Because the slope of the tangent line to the curve is always like 5 or up. So it means like this, if you think about the tangent line as kind of telling you what the function's doing, it means the function's moving up all the time. Why are you looking at me like that?
I have that for a quartic.
Oh, well in fact it's a quintic.
Oh, that's true.
Yeah.
Oh, yeah. Oh, okay. Yeah.
Ooh,
Yeah.
So it must be doing something like, for example, if you plug in 0 into this function, you get 0, right? And the slope at 0 must be like 5, right? So if you think about what this function's doing, it's got to be kind of like something like that, right? Because there has to be a tangent line of 5 at 0, and the derivative is bigger even everywhere else. This function's just not slowing down. All right, more on that over the next 2 months. 77 I thought was again a multi-step problem. 77 says, his wording was a little bit awkward, but what it essentially boils down to is, take this function, f of x equals root x, and find the equation of the tangent line to the graph of this function through the point -4, 0. So, find equation of tangent line to f through the point -4, 0. Calling out for a picture, demanding a picture. If anyone attempted to do this problem without a picture, you are literally crazy, and I'm taking away your math license. Because it's like driving with your eyes closed. Okay, let's make a graph. What does it look like? It looks like this. And then let's make a point over here, -4, 0. And now immediately I see what's going on. There's a nice happy tangent line. It goes through the point -4, 0, and it intersects the curve like maybe here or something. Yeah, if you did the problem wrong, it's probably because you didn't draw a picture, right, Yal? Did you draw a picture?
I thought it was. Never mind.
All right. Good. Some people ask me, people ask me, Mr. Rose, how'd you get to be so smart? You know what I tell them? No, never ask me that. I draw pictures. Okay, good. So, yeah, it's the right answer.
I mean, yeah, that's like a weird answer.
Okay. Tell me some things that I know. Rohan. 1 + 1
Well.
= 2.
The slope is positive.
The slope is positive. Okay, more specifically. Tell me things I don't know. Let's do that, Ron.
The location of that point, which is...
Yep, I sure don't know. That's the whole point of this problem, is finding it.
Just take the
Cindy's getting impatient. She says, let's just take the derivative. Okay, we can just do that. I don't feel like I need to yet, but you know, probably that's going to be relevant somehow. So what is this function? This function is root x. Note how I first rewrite the function in derivative-friendly form prior to differentiating. Now I use, again, not only have I not proved that the power rule works for negative exponents, but I surely have not proved that it works for fractional exponents. In fact, we used the binomial theorem, so you should be feeling a little bit angry at me right now for just telling you to use the power rule. But anyway, it definitely works. So if I do the power rule says drop down the power and then like subtract 1, so we get that. Yeah.
Yeah.
This is what you guys did basically. It's not so hard. As long as you trust the formula. So thus the derivative of this function is 1/2 root x. Okay. All right. So what? Calvin.
Make an equation of that line using the -4, 0 as kind of your basis. So like, set up like the equation for that line.
A little bit more specifically.
Tangent line.
I have like
Using this, because you have the slope and you have a point on that line, so you might.
Do I? I mean, I have drawn a point.
No, -4, 0.
Yeah.
Is on it.
Yeah.
So you can make the.
Yeah, how about we label the point? Thanks, Ethan Chen. What would you like to call it? B.
X, Y.
B.
No.
I don't know, he wants to call it B.
No,
So,
B root B.
so this is B comma root B. I actually think it's better to not use X and Y because we think of them as variables, whereas this is not a variable, it's like an unknown, which is a slightly different, subtle difference, but it's a number which is not changing, it's simply a number which I don't know the answer to. So I like to use the early part of the alphabet for that, and so should you. Alright, so Calvin, now that I have points, okay, now I can actually kind of do what you said a little bit, right?
Yeah.
Yeah, in fact, can we just get right to this? Sandy, tell me what's going on. What do we do? Can we just do this?
Now you have to.
Did you do this problem?
Yeah,
Did you get it right?
I think so.
Feeling good?
Except, yeah, so,
Fine, he's fading. Giovanni, help. What should we do?
Tangent line. Yeah.
Find the slope, okay. What is one way to find the slope of this line? Yeah, we can just do like algebra 1, 2 points, right? It's just change in y over change in x. So if the slope is just change in y over change in x, then on the one hand, the slope is going to be root b minus 0 over b minus -4. And so we get root b over b plus 4. That is definitely a correct answer to what the slope is. Yet on the other hand, Sandeep,
the derivative is the slope.
on the other hand, the slope of that line is the derivative of the function at that point, sort of by definition. So on the other hand, the slope of this line is just f prime of b, and as we have previously calculated, the rule for the derivative, f prime of b is, well, you just plug it in, it's going to be 1 over 2 root b. So in fact, this maybe is kind of even easier than the previous problem, because there's only like one sort of unknown variable. There's no system of equations, it's just a straight up slope equals slope. So I get 1 over 2 root b equals root b over b plus 4. Now I need to kind of do some algebra. So cross multiply. I just assume everyone's like perfect at algebra at this point. But this is pretty easy. And I guess I get like b is 4, right? Did I do that right?
Yep.
B is 4. Bam! And I should see if that actually seems reasonable. If that's reasonable, then that means that that point is 4, 2. Is that correct? Well, now what is the slope of this line as calculated by rise over run? It would be 2 over 6. It would be 1/3, right? Is that right?
Right.
And on the other hand, if I plug 2, wait,
No.
No.
let me try that again.
Oh, no.
8. 2/8. Yeah.
One.
Did I do that right now this time?
Yeah.
I did.
Yes.
2/8, which is 1/4. On the other hand, if I plug 4 into the rule for the derivative, I also get 1/4. So I'm feeling pretty good. All right. Let's do one more problem. Should we do 113 or do we not have to? Do we do it? Let's do it. I think I can do this kind of fast. 113 says, it gives you this piecewise function, f of x equals ax cubed when x is less than or equal to 2, and x squared plus b when x is greater than 2, where a and b are unknowns. And here's what it says. Find a and b such that this function is differentiable everywhere. Okay, talk to me. Has to be continuous.
Yeah.
Okay, first of all, this man says that we proved that differentiability implies continuity. The contrapositive of that is if it is not continuous, then it is not differentiable. So, actually that was a useless piece of logic I did there, because what I really want to be true is I want it to be differentiable, thus it must be continuous. So the pieces have to meet, right? That's what you're saying, right? So if the pieces have to meet, then on the left, I don't know, what should I call this? Like, let's call this f of 2 minus or something like that. F of 2 minus, or I guess I could just call it f of 2. Yeah, what is f of 2? F of 2 is just going to be 8a. Do you agree?
Yeah.
All right, and then what is the limit, I guess if I want to be technical about this, what is the limit as x approaches 2 from the right of this function? Well, it's the same as the limit as x approaches 2 from the right of x squared plus b, and well, what is that?
4 plus b.
4 plus b. Yup. Varun, can you erase the backboard? So if this is true, then my conclusion is that if this piecewise function is in fact a continuous one, it must be true that 8a is 4 plus b. Okay, good. More things.
We need
To
to
mean
solve
something
for
else.
The derivative of ax cubed and the 2 should be the same because they're like the same.
Yeah, at 2 though, only.
At 2.
At 2, exactly. Yeah, I'd like to talk about this as like a, if you have a, what's it called? Track team. Does anyone run track here? What kind of track do you run? Distance? Distance, okay. What kind of distance? Like by yourself or the relay? Oh, okay, good. Relay. So I'll say some things, and then you correct me if I'm wrong. So my understanding from watching the Olympics, even though I've never run relay in my life, is the whole point, this is actually not advanced, this is just common sense. Duh! The whole point of relay is you're supposed to run really fast. Then also, when you hand off the baton, you have to do it like in the exact way, so like, how would you put this? You want to be running at the same speed as the person as you pass them, right? That's kind of stupid, right? Obvious. So if someone's running, you don't want like a bad handoff. In a bad handoff, someone would have to like slow down first, and it'll be something jerky or something like that. So it's like the same thing with these two functions, right? It's not. We don't only insist. Okay, if the two functions are continuous, all that means is that the handoff happened, right? It means that the two people running the relay were actually in the same spot at time 2. Rohan, you with me? But that's not enough. We don't want it to be a jerky handoff. We want it to be a smooth handoff. And in order for there to be a smooth handoff, the rate at which this function is increasing at the exact time t equals 2 of the planned handoff has to be equal to the exact rate at which this function is increasing, so that the functions just smoothly glide into each other like a nice relay handoff. Okay, so for this we must invent some new notation that I'll just invent right now. And that is the notation of what is this function doing just to the left of 2. So let's call it f prime of 2 minus. F prime of 2 minus is just the derivative of the function as x approaches 2 from the left. Follow? Okay, well what's it going to be? Well, if I'm less than 2, then I clearly follow this rule, right? So the derivative at 2 minus is just going to be, well, yeah, it's going to be 3a x squared, and then we plug in 2. This is like another new piece of notation, which just kind of says, this just kind of says 3ax squared evaluated at x equals 2. All right, if you don't like that,
No.
doesn't matter. So you get 12a. Is that what you get? If you just do the whole thing in your head, you just get 12a.
Yeah.
Whereas the derivative from the right of 2 is going to be, well, now I follow this rule, which says that it's just 2x. So the rule is 2x, and then I evaluate that rule at x equals 2, and I get 4. So in order for the two things to meet, it must be the case that 12a equals 4. So a has to be 3. Everybody with me?
A is 1/3.
Probably like 1/3. Glad you guys are here. Important part of the team. 12a equals 4, so a is 1/3. So if a is 1/3, then it's like 4 to 8/3 minus 12. B is negative 4/3. Bam. So good done. Okay, good. Can I have this homework?
I'll do it this time, guys.